In this video, I'm going to talk to you about fascia, or the collagen fibers, and the system of fascia and the gel and the different products that part of the body that go along with healing the body with vibration. And the VFRT portion of this, the Vibrational Fascia Release Technique, really makes sense to have a better understanding of fascia from at least from our standpoint, to understand what it is that's actually changing when you're putting a tuning fork, when you're pressing a tuning fork down on the skin. What is it that you're palpating for? What is it you're feeling? And what I'm about to show you has a very detailed look at fascia itself so that you can understand it. What you're currently seeing on the screen on the picture is actually something that we did here at NEHC with our own research. We took an endoscope. You're going to be able to see a picture of that. We did some studies. One of the challenges that we have, especially for being a training facility, is showing some of the things that we usually see in fascia research, which is doing cadaver studies. That's not something that everybody is ready to see, and we had a very difficult time showing fascia from the standpoint of the fascia researchers. And looking at a cadaver study and seeing the human body dissected in different layers the way the fascia researchers are doing, it's very difficult to be able to put those pictures and images and video out for being able to train somebody on that, because again, not everybody is ready to see those sorts of what would be considered graphic images by some people, or some of our students that have said that they were gross and didn't want to look at them. So that kind of prompted us to do our own study so that we can show the same sort of fascia, to be able to take the tuning forks and actually apply it to fascia, and we can see what it looks like. And what you're going to see are some of the images that we took from our first study with the endoscope. Was looking directly at a steak that we bought in the store, and it probably had been frozen at one time. What we were doing is it's basically just a beef roast, and we were separating the different layers of muscle and meat, and we were able to see the fascia fibers, which is the image that you're currently seeing here, is still intact when you have a steak that you're buying, obviously before you cook it. When you cook it, then the fascia and the fat and all that ends up dissolving. And then we ended up doing another study where we went to a processing facility in our local town, and we were able to obtain the upper layers. So the problem we have with steak and with beef that you buy in the store is that they actually remove the outer layers, and those layers are pretty important for us, especially when we're using the tuning fork, and you strike the tuning fork and you put it down on your skin. Most healers are looking at the muscle, the tendons, the ligaments, and the things that are musculoskeletal, the bones. And what we've found, that when we use our VFR techniques, we're palpating, we're putting the tuning forks down, we're pressing down, the ability to have things change, collagen fibers, the fluid that goes along with it that's pressurized, that we're really dealing with the top half inch in most cases. It's going to be different depending on what part of the skin, even the underside here. It's very difficult to go and get a steak from a store that hasn't been cooked yet and spread it apart, take a look at things without some of the other things that are that are already gone. Blood has already been drained. You're not able to see the gel, not able to have a really good picture of what's happening in that first half inch. And so we ended up doing another study, and you're going to be able to see pictures of that as well. One of the things to look at on this picture is What I did here is the endoscope, the camera was magnified by about 2,000 times, and you're able to see these little fibers. And this is what we actually call collagen fiber. This is what most people refer to as fascia. And one of the things that's pretty important here to look at when it comes to fascia itself, I'm actually going to draw on the screen here. I'm just getting my line tool here. Notice that you actually have some very interesting things happening. Now, this is just the layer in between. You know, if you were to pull a steak apart and you get the layers that are kind of tough, it's actually what makes what makes everything so tough in a steak. You have these little fibers forming here. I'm going to zoom back out again. Okay, so now I'm zooming back out. I need to go back into that drawing tool again, I think. Get that thing back. Alright, so I had originally drawn a line like this. That's a collagen fiber that's being stretched, really. Then you're noticing, you might notice that there are some triangles forming here, and that's a very important thing for collagen fibers, because what they're designed to do is control the structure of your body. And these collagen fibers are found all throughout the body. They used to be called connective tissue, and some people still do. And it's something that over the past, as we learned about anatomy, some people went directly into studying the human body several hundred years ago, and we took a butcher approach. We ended up cutting through things and throwing a lot of this material out that seemed like it didn't have a purpose. And over the years, it really didn't gain a lot of really focused study until just recently. A lot of the study we do now, we have the ability of putting cameras in and magnifying and seeing things live. There are videos out on the internet where you can see, Jean-Claude Gimberteau has videos out where you can see, he's a hand surgeon. He was able to put an endoscope underneath the skin and actually see how things are moving, very much like the pictures that I have here, understanding the fact that he's showing live footage or seeing a person live as things are moving, whereas the pictures that I'm showing here, you're obviously seeing something from a cow. So there's a little bit of difference there. But you end up seeing some things here. You're able to see the collagen fibers with you know, it's magnified, but you're able to see it with your eyes. You're able to see all this other stuff that's happening here. What looks like looks like water. This is gel that's happening so the fibers are inside a layer of gel, and it's actually a layer. We're going to talk about that. That's another product that happens. Proteoglycans, glycosaminoglycans, the products that are needed for this structure. We're going to get deeper into that as well. Just going to move to the next slide here. So fat cells, fiber, and the gel that I was just talking about. Here's another look at the steak itself. So again, we're just seeing the area in between two layers of muscle in a beef roast. And if you look at the top image, let me see here. I'm going to switch over from a line tool to an arrow just so I can show you that there's some things happening here that are still available. You know, that are still available in this picture. And you can see that there's all of these little balls of something. These are actually the fat cells that are still available in a steak. You know, when we cook a steak and we get the real good flavoring in a steak, this is really what brings a lot of the flavoring, the oils that come out of this. This is the same sort of fat cells that we have in the human body. Same type of fat cells. and notice how they're all kind of clumped together, and the fibers run through those layers as well. In the bottom portion of it, you again are seeing the these little layers here that are wrapped around and supporting the collagen fibers as the collagen fibers are being stretched. So so it's good for you to understand this interaction between the different substances that are happening in that first inch or that first half inch, maybe up to an inch in the human body. Understanding that, you know, when we get to cows, their outer layers are a little bit more thick. They have more fatty layers, and that's really we can apply these concepts through the entire body. These collagen fibers, the fibers that you're seeing here, they're making up pretty much every structure of the body. And they don't always look like this. This is really the outer layers and the layers in between the muscles. They're wrapping things. They're creating structures. They're creating the ability for your muscles to be able to move a certain length, and then they tighten up from the tendons. Tendons are made of these collagen fibers. The vessels that you have in your body, the structure of those vessels, made with collagen fibers. Your organs themselves. There's a lot of research going on right now, the plastination projects that are happening throughout the world. They're able to take the let's say the heart. They're able to take the heart cells inherent to the heart, and they're able to dissolve those and dissolve the materials, those particular cells. What you're left behind with is a heart structure that was created by collagen fibers. So they were able to dissolve one substance and leave the other substance, the collagen fibers, behind. And you're actually left with what would be called a ghost heart. And then that plastination project, one of the things that comes out of that is something like the ability to recreate collagen in some way to where you create another organ, or do a 3D printing with the right substances to create a heart, and then reintroduce the person's own cells back in and recreate an organ. So those are some things to think about, that your organs, the vessels, the layers in between, the bags that separate things, those are all made with collagen. The collagen fibers and the things that go with it. Fat cells are in the outer layers usually, but it's throughout a lot of different layers throughout your body as well. So what you're seeing here on the bottom left is what a collagen fiber starts out to be. So collagen is a substance, and that substance is created, as you can see in the picture, it's created by amino acids. And all of that is that what would be considered collagen fibers actually are creating themselves. It's what's called self-assembly. And you can see that as the amino acids, so there's a certain substances that are combining themselves together into what would end up being a triple helix. And you see that in the center picture here. And what a triple helix basically means is that as those amino acids are basically attaching themselves to each other, it's kind of like maybe extruding itself. And I'm going to show you the fibroblast cell that actually has the materials to build these amino acids, or the amino acid chains. And what they end up doing is assembling themselves into a triple helix, and it looks something like this. And the triple helix, basically, you're creating a triple helix that continues to rotate into a helix pattern, and then you end up having basically a fibril, and all of these little triple helixes will combine together, and you'll end up having a fiber. So there's several of these all together, stacked together, And then what you're actually seeing on these pictures are several of these stacked together in what would be a fiber. So these are the pieces that make the fiber themselves. And then, collagen has the ability to be stretched, and it has, the ability to withstand tension, which is, the reason why we have a structural device like that, or a structural fibers. So keep those things in mind, that what we're dealing with is just amino acids that have been put together in a certain way, and there's a triple helix, a little rope-like substance. All of those are combined together, and then we end up having an actual fiber, which are the things you're currently seeing in the upper picture. So the cell that actually creates the material, this is called a fibroblast. And this is it's not technically a specialized cell, but what makes this fibroblast cell so different is that it's movable. It actually moves around. It's mobile. It goes where it needs to be. So when we're looking back at a structure like this, even in the upper left-hand corner of that picture, the ability to create those fibers doesn't mean that there's cells inside of the fibers. The fibroblast is kind of like, I consider it like a spider in a spider web. The spider web and the spider are two totally different things, and that spider can spin this web as it needs to because it has the substances to create that three-dimensional structure. And the fibroblasts do those things. You can see that there are other substances that happen that are products of the fibroblast, enzymes, the extracellular matrix, which I'm going to talk to you about that. That's actually something that gets created that provides space so that we can have cells living in that space. We can have interstitial fluid, plasma from our blood flowing through that space. The collagen fibrils, which I just showed you, those are being extruded or created from the fibroblast. And then elastin is very similar to the collagen fibers. Elastin is a little more elastic. It has a little more of an elastic property to it than the collagen fibers. Growth factors and hyaluronic acid. A lot of people are talking in the research, fascia research, about hyaluronic acid. Sometimes you hear it along with collagen, where if we have more hyaluronic acid or collagen in our face and in our skin, that things will be better, and it makes our skin even better. We'll get to those sorts of myths in other videos. But the hyaluronic acid is part of the fibroblast substances that come out, very important for lubrication and things of that nature. It's used for a lot of different things, but there's a lot of research going on with what types of cells create hyaluronic acid, or are there specialized fibroblast cells. Carlos Stecco has done a lot of research on hyaluronic acid as well, and has come out with a lot of things that she's talking about with dedicated fibroblast cells specific to hyaluronic acid production. So there's a lot of information out there when it comes to fascia, but at the center of the fascia study is the fibroblasts. The fibroblasts, which are these are the ones that create the fascia part of it. So if you think about the bones are actually fascia-like. They have osteoblasts and osteoclast cells that do very much the same thing that the fibroblast cells do. Create or take away the substances, build on or remodel and take away. So you have bones that get created where there's more bone density, or there's bones being built and grow and repair. The same sort of process happens with our soft tissue with the fibroblasts, and of course there's a structure in place for the ability to remodel these the fibroblast, not the fibroblast, the collagen fibers themselves. So this is the builder. There is a process to take the collagen fibers and dissolve them so that we reuse, we constantly recycle and remodel our body. And this is going to come in handy when the tuning forks are known to actually have a vibration, stretch, and vibration can actually tell the collagen fibers to remodel. So that really helps within VFRT. What you're seeing here on this picture is how some of the collagen fibers, when they're created, you were seeing a lot of triangles before, and those triangles were just, you know, stretched collagen fibers, and you see how they were oriented. That's actually pretty important in the orientation of these fibers. So in our outer layer of our skin, we have a couple different layers, which I'm going to show you in some slides coming up. We have different needs for different tension in our body. We're trying to hold our body upright in certain postures, and our fibroblasts and our fascial layers are trying to keep into a certain integrity. And sometimes it's the orientation of those fibers all pulling in one direction, like you see in this picture here. Pulling in one direction, that would be make sense that those would be tendon type of materials. So tendons are created from fascia itself, but the fact that they're all oriented together in the same direction gives you a really good tension capability and a stretch capability in one direction, but it's not so much in crossways direction, which is where you end up getting some rips and some strains and things like that. Actually, I'd like to show you this picture here. So when we look at collagen fibers, it really depends on those substances, those 3 amino acids. You can start to build those things up, and you know, they might start out as substances like this, and then three amino acids are going to connect together, and they're going to be held together by ions, basically. And depending on what's in each of these 3 substances and the successive building up of the fibrils themselves, when you start to swap out the substances, you start to change the property of the fibril and the fiber itself, how much it can be stretched. Are you creating elastin? Are you creating a more fascia type of fiber? Really, it has a lot to do with how far can something stretch. Like this is identifying that there are sometimes fibers that can be stretched, and then when there's no more need for the stretch, when it comes back into place, it still maintains some sort of length to it. So some of the fibers in your body, depending on how it's created, they don't always go back to their normal length, and they take a little bit of time to be able to readjust. So sometimes it's the substances and the collagen fiber type that really determines what is happening and what the needs are, the tensional load needs are throughout the body. And this is just one example of how the fascia knows to orient itself in addition to the substances that create these different fibers. Those are important as well to know. This is also a different way of looking at fascia, and it's very much like the picture that I showed you earlier, where you see these fibers at different angles, and what you're seeing here is something that's not so dense. You're able to see some holes in between the fibers, and this was probably stretched out a little bit. But what you can see here is the red stuff that's moving up through this three-dimensional layer, and you really have to see this from a 3-dimension, kind of like it's a web work of some sort. And one of the things I want to talk about when it comes to 3 dimensions, and I know sometimes we think in you know, there's this web work, there's 3-dimensional fascia layers. I just said layers, so 3-dimension and layers, they don't seem to coexist or be the same exact word. And that was something that I had always thought, that fascia had 3 dimensions to it, and there was always a web-like structure. Well, we also have to think in the layers that slide across and past each other. Those are pretty important too. And it might not be so easy to think of fascia in the format of the picture that I'm showing you here, where it's all 3-dimensional. It's not always that way. From a micro view, those fibers that cross each other, yeah, they are going in different directions and they're pulling on things. They're causing tension. They're doing those sorts of things, but it's sometimes those fascial areas are in very flat layers if you look at it from different standpoints, and that's what we're going to do here in a little bit. So it's good for you to understand that these fascia fibers can cross each other. There is some intelligence to what looks like chaos. You have to figure that these blood vessels that are running through these layers, they have to be able to support the ability for movement in your body and still keep the flow of fluids through these areas. How would it even be possible for you to bring blood from your cardiovascular system up to the very top layer of your skin and still have the ability to stretch your skin beyond what you think is normal? So those are some important things to think about, and how interesting this fascial structure is to our body, to be able to allow for sliding, to be able to allow for things moving through those layers that could end up getting pinched or flow being reduced because something's wrong there. The fascia fibers are messed up and there's fluid in there pinching things off, and there's pressure involved in there. So these are some important factors that we think about in VFRT. Is what do the structures look like? What is the fascia there for? There's a fluid component to this as well. And there's some gel there as well that really helps for fluid flow and for structure itself. In this picture, this is just another picture of our studies where I'm kind of zoomed in looking through. There's some depth there. This was in, I'm about to show you a picture of the second study that we did, where we ended up going and getting materials, that upper layer, the superficial layers of the body, which was a cow. And we were able to look at things. What you're seeing on the left-hand side of the screen, it looks like there's some blue something or other, or bluish green. That was actually me introducing some dye to the materials and seeing how everything worked. One of the important things about our second study is that we were able to gain the material or gain access to the material for us to do the study on. We're talking the upper layers, the outer layers of a cow that is removed in order to get to the meat. That's something you don't usually see in the supermarket. The upper layers, from the outer furry, hairy layer of a cow all the way into the first layers of muscle. All that stuff gets removed and you never see that stuff. Well, that is what we wanted to look at in our study. So what you're seeing here is, when you look through the fibers, you see the red streaks that are happening there. That's obviously the cardiovascular system. And notice there's some parallel lines there. So I'm going to show you some things here in a couple pictures a little bit later in this video, where you're able to see how the body deals with running the cardiovascular system through something that's going to be moved quite a bit. I mean, imagine when a cow walks or moves or lays down, that the stretching involved at the outer layers of the skin is pretty dramatic. Our skin can only stretch so far before the body actually creates these collagen anchors that keep our skin from moving too far, and then we end up we end up hurting our cardiovascular system. So this is what you're looking at. This is actually underneath the skin, looking up towards the very outer layer, which would be the epidermis of a cow, which would be a very, very outer layer of our skin. And this is just another picture where you see the collagen fibers. Again, I'm stretching some things here so you can see the fibers, but normally they're within certain layers. You're seeing air and you're seeing things around these fibers, and we don't have very much, open air spaces in our body. They're all very compact, and they're very, there's a lot of layers there. The blue areas that you're seeing on the left and the right, those again were areas that were dyed with a blue dye. And you're able to see inside of those layers. If you look on the left, you can probably start to see what looks like little bubbles. And remember that I showed you the fat cells. We're going to talk about fat cells here in a minute. Those fat cells are inside those layers, but how do they all stay together? It's still fascia. Remember that most structural things are fascia related. So we not only have the fibers that are holding structures in place, and these are tensional supports, just like you would have in a bridge or something that's cable related. And there's a tensional integrity. We call that tensegrity. And we actually have studies of biotensegrity, which is where these fascial structures and structures of our body, from the outer skin all the way into the insides of our cells, to the nucleus, where tension and vibration and you pressing on the outer layer of your skin or putting a tuning fork and pressing down on top of the skin actually transfers that information and that tension all the way into the inner side or insides of our cells. We call that biotensegrity. And these fibers and the way that they're oriented really have a lot to do with our ability to communicate, especially when we're dealing with mechanical vibration. We can communicate that vibration all the way into the insides of our cells. So here is the second study that we did. You notice that this looks like I believe that would be considered hair. We actually obtained these samples, these two samples, so what you're seeing is within an hour of the cow being alive. So the fluids, we wanted to be able to capture the fluids that are still inside the interstitial space. What you're seeing, obviously, since you're seeing the hair there, that is the very outer layer, what would be considered our epidermis. And then you see what's directly underneath the skin of a cow. That is very much the same way that happens with us. Just underneath our skin, our epidermis, we have a dermal layer. Sometimes they're called different things, and there tends to be a little bit of confusion with terminology depending on who is looking at our body. They tend to call things a little bit different. The interesting thing that most of the things that are happening that are going wrong or going bad, we tend to think of musculoskeletal. The muscles are going, there's something wrong with the muscle. There's an impingement. The muscles aren't working. The nerves running to the muscle. The trigger points inside the muscle groups. We tend not to think about the upper layers, the superficial layers of our own body outside of the muscle group. It's not to say that the things that could go wrong with a person's body, whether it's motion, range of motion, or whether it's pain, that could be inside the muscle groups. But we tend not to think about our outer two layers and that the fascia that's happening in those layers, look at it. It's just a big blob of fat. We actually call this white adipose tissue. It's our superficial layer, meaning it's closest to the outer layer of our skin. And if you look here, I'm going to do some drawing or put some arrows here. So if you look at, oh, went the wrong way. All right, ignore that arrow. So if you look right here, So this is what would be considered our superficial adipose layer, as opposed to our deep adipose layer, which is, you see the other layer right there. The interesting thing is that our body is created just the same way. It's structured that way. We have a very, very outer layer, or our epidermis, and then directly underneath that, it's actually very difficult to remove these layers. These are very thick layers. There appears to be a three-dimensional component there with the collagen fibers, but think about all those different fat cells that are in there. They're layered together. There's a larger layer of white adipose tissue in our outer layer, and then there's fascial layers. There's sliding layers. And then there's another layer of deep adipose tissue, which is what you're seeing in the upper left. That's more of a brown adipose, and there is some slight differences between the different fat cells, and those are very important to us, especially in vibrational fascia release. So think about this. If you were to dissect yourself and you were able to see what's happening underneath the skin, these two layers right here, even though they look a lot thicker on a cow, these are the top two layers of our skin. The next thing down from these two layers would end up being our muscles, or in our abdomen it would end up being open fluid spaces, and then our organs themselves that are in our abdomen. Or you might have a bone layer or something like that. But this is what covers most of our body. These are the layers that we focus on with vibrational fascia release. Sometimes we think that it's the muscles and the things happening inside the muscles, but what we've learned is the things we're feeling in palpation are coming from these layers. And how we know that is the fluids that we're removing that's been pressurized and causing pain. We can actually slide those fluids and vibrate them out of pressurized spaces here in these two layers and move them along into long runs of the body that wouldn't make sense from a musculoskeletal situation. If the fluids and the problems were within inside the muscle groups, we wouldn't be able to move them in the directions and the length that we can with VFRT. So this is what we're looking at. The outer, very outer superficial adipose, which is nothing more than fat cells, they're all combined together in one very thick layer. We're going to talk a little bit more about that, but I wanted you to get an understanding of what you're seeing there. Then between the superficial adipose layer and this layer right here that I'm looking at, there's a layer of fascia. It's a sliding layer to allow these two layers to move back and forth. As you're moving your muscles, as you're moving your body around, these two layers need to be able to slide past each other. They're still made of fat cells with a lot of other gel fascia that's surrounding the different fat cells. And then, of course, there's the cardiovascular stuff that's running through these layers that you're currently not seeing right now. Your veins, your arteries, and the lymphatic system, your nerves are all running through these layers. So as these layers have problems, so does our body. And I'm going to show you as we get through these things where the fluids that are there that are coming out of your cardiovascular system has to diffuse itself and run through these layers to feed the tissue so they can live. What you're able to see, let me get out of the arrow here, and I want you to, all right, I'll do freehand here. What you want you to take notice is on the glass itself, because the adipose tissue still had fluid there, if you notice, there is some of the interstitial fluid, which you can see is clear, is starting to seep out from this layer. So there is fluid there. This is where your cardiovascular system pumps out or seeps out or comes out through our capillaries. They come out into this layer. So there's fluid in there. There's plasma. It's the blood without the red blood cells. So that fluid in there is really what we focus on. When I say fluid, this is what I'm talking about. Some of it just happened to have seeped out in the very, very outer layers, but there is some integrity to this layer. You can see that when I laid it on the glass, it's able to stand up. It's able to have volume. This is because of not only the fat cells, which are surrounded by collagen fibers, but the collagen fibers themselves. They're able to keep a this is really your extracellular matrix. You're seeing it in a different view, and even in the brown adipose layer that you see just behind it, that has a volume to it that needs to house all these things, from the fat cells to cardiovascular system, nerves, lymphatic, which is part of cardiovascular, and it needs volume. It needs the ability to have the plasma coming from your blood system to be able to diffuse through those layers. So this is a picture of what it looked like during our studies. You can see that I'm injecting some blue dye. All that was for us is blue food coloring, and I was injecting it just to see how fluid can diffuse through these layers, how long it takes to diffuse through there. Because imagine that you have plasma coming out of your cardiovascular system, your arteries, the capillaries, or seeping through the walls. It takes a while for substances to diffuse through the layers, and this gave us a good idea of how things, how long it takes, and where does the fluid get trapped. And didn't quite know what we were going to be able to see here, but we're able to see certain things running through the layers that you normally wouldn't be able to see. Some of the blood has already been drained from here, but the interstitial fluid itself is still very much a part of these layers, and they're really kind of trapped in these layers. So you can see the endoscope, which is, I think this is 2000 times zoom, and some of the pictures that you're seeing. So here is a picture, cross-section of what's happening underneath our skin, with the very top being the outer layer of our skin, and this happens to be a layer that has hair on it. And that's actually pretty important to know what parts of the body you're looking at, whether it actually has hair on it or whether it doesn't have hair on it. That actually changes the way that the sensors underneath the skin work as well. The challenge here with looking at skin is when you look at three-dimensional pictures like this that are trying to show what the skin looked like and the different layers of the skin. Every time I look at these images that try to represent it, they all look slightly different. And the important thing here that we're looking at, that I want you to understand, is that you have this, let me get back to the, I'm going to get back to the arrows here. So this very outer layer of the skin, you're actually going to see on our video or on our pictures that we did, you're able to see those things. They're more white in nature. And the adipose starts to get more yellow. So that's what you're seeing here with the adipose layer. And you notice how it just starts at some point, like right here is where the adipose starts. That's kind of different, and how thick those layers are depends on, of course, the animal. A cow is going to have a much thicker outer layer, and then you're going to have these little fat lobules. This is what happens. Our entire body, with the exception of maybe 5 different locations on our body, has a fat layer just underneath our skin. That is called the, well, okay, so you see here that the very outer layer is called the epidermis. That has no fat to it. And then there's this transitional layer that tends to be different depending on who's explaining it. We call that the dermis. And you can see that it's a layer that has some transition into the fatty layers. And then the hypodermis is where the fat is supposed to be living. And then you see that there are nerves that are running through here, coming up to the surface, so that we have all of our sensors in the outer layers. And then we have our blood system, our cardiovascular system running through there. Notice how they're in parallel. What they try to do is to have what's called a plexus, to where they're running horizontal to your outer surface of the skin, so that they can stretch as you stretch. They can move left and right without having to worry about it. So these plexuses are long runs of veins and arteries and your lymphatics, which they rarely put on here. And then there's these vertical runs that run that blood up to the next plexus closer to the outer layer of your skin. So you can see that they're running through the adipose layers. And as you move and as the adipose gets bigger and bigger, so as you start to gain weight and fill those fat bubbles, then you start to have problems. Then what they're really not showing you here is in between these layers, you see that white stuff, that is actually collagen fibers that are in sliding layers. So imagine the top half of this above that arrow that I just put on there. The top half can slide past the bottom half in a sliding layer. This is really our superficial fascia layer. And that's important to understand, that even though we say that there are fascial layers, that there is fascia in our skin, in our body, that some of them are just in sliding layers. So, and then you're supporting the top part, which is the superficial adipose, right here, a bunch of fat cells. And then underneath that are other layers of fat cells. These are the brown adipose, which act slightly different, is used for slightly different things. And then we have the muscle layer itself. So there are several layers of fascia that are nothing more than collagen fibers. Those are what you saw in a couple of the pictures where I was separating the different layers of the muscles. And in fact, in between the different muscle groups, you can see that there are other places there. Those are the fascia fibers, collagen fibers, that are separating the different muscle fiber groups. That's really what you were seeing in that first set of images. As they were pulled apart, you were actually able to see the collagen fibers in between them. So this is what we're looking at with basically a cross-section of what's happening underneath your skin. Some things are left out, and it's very difficult to understand that there are structures happening here that are keeping our skin from moving too far. There's collagen fibers that are really making up this whole process here of from our muscles all the way up to the outer layer of our skin. This is just another way of looking at a little more three-dimensional. You can see that you have that outer dermis layer that's a little more white-ish and kind of transitions down into where the adipose layers. It's really difficult to pull those layers apart. If you notice in the pictures that I showed you a little bit earlier, that you know, if you were going to process a cow to make the meat ready for sale, we usually see the after effects of that, cutting the different muscle groups out into steaks and different types of products, meat products that you would have from the supermarket. These layers have already been removed, and they actually remove quite easily if you pull back and pull back these layers. They're able to remove themselves in different strips. So you saw that you had the top layer, which was the superficial adipose, that was able to remove itself very easily in the sliding layers in between those two. You're seeing again the very top layer, which would be the superficial adipose, which would have been already removed from the deep adipose layer. So you see again, I want to point out that your cardiovascular system runs right through that, and your nervous system. And cardiovascular is still including the lymphatic system, which once again has been left out of this equation when we do three-dimensional rendering of what's happening just below our skin. This is another look at the very top there. You can the very top of our skin. The very top of the picture would be our outer layer, and then of course the yellow part, you're starting to get into the transition, what would be the dermis layer. Again, I wanted to point out in this one, this rendition, that you have plexus, a cardiovascular plexus, and that would be the red would be representing the arteries, and the blue would be representing the veins. That's bringing our blood up to the very surface, the outer surface of our skin. And then in between those areas, you see those little yellow balls. That's representing the fat cells, the adipose. Anytime I say adipose, that's really what I mean. It's a fat cell. And I'm going to show you a couple pictures of fat cells so you understand what they look like. They're kind of, here it looks like they're all nestled in between those vertical runs of your cardiovascular system. Remember that these things have to be able to move left and right and horizontally and being pulled on, and whatever kind of crazy thing you do with your own body, you still have to be able to maintain that structure and get the blood to the outer layers of our skin. And this is how that cardiovascular system plays out. The important thing that's kind of left out of here is the fact that you have those fat cells, and you saw earlier that that's all really one big compact layer. Looks like there's a lot of space here, but there really isn't when our cardiovascular system runs through our fatty layers. They really get compressed, and they get fluid gets pushed out of our cardiovascular system into our interstitial space. And that's where a lot of our movement and our problems with pain, because there's pain receptors here that are being compressed, and we have problems with our nervous system. So a lot of the problems are happening in these outer layers of our body, outside of the muscle layer. Again, I say that, but I want to point out that even though I'm saying the outer layers, there are still some problems that can happen within the muscle layers, but that has had those musculoskeletal layers have already had so much focus on them that it's good to take a look at these outer layers that have been ignored all these times. And we can feel what's going on in these layers when we palpate and understand where to put our tuning forks. And we know that we're having an effect on these outer layers as well, towards range of motion and towards pain relief. What you're seeing here is an actual human rendition of what's happening with the very outer layer. So if you look here, this is what would basically be the very, very outer layer of our skin, the epidermis. And you can see how that starts to transition into the dermis layers. And of course, we're going to move all the way to the fat cells. So this is the type of diagnostics that we can take a look at cross sections, and what you're able to see here. And I'm going to be showing you additional histography. This is where we're able to look at certain parts of the body and to be able to see what's happening with the body. Usually these slides are from live people. You're able to see certain things like here. These are those cardiovascular components and the nerves. You're able to see those things play out here in this upper layer. So now you can see from that three-dimensional thing that I just showed you, the three-dimensional representation, you're able to see the transition into where the outer superficial adipose layer starts to transition in, but still there's vessels running through the adipose layers as well. These are fat cells that have been pushed in. You can see that this person has some obesity problems because you see different fat cells that are much bigger than other fat cells here. This is just a way of seeing the body. That's not working out too well. This is just a way of seeing the body from a different direction and different angle that we wouldn't normally see. Here's where you start to see problems with what causes us to have pain and mobility problems, is by looking at histography slides like this. This next slide is just to show you that bottom layer. This is the brown adipose tissue layer. And again, this is one thing that is able to be separated from the muscular layers underneath it, just because that's where those layers would remove quite easily without having to cut through this. Remember that a lot of these layers were considered not needed when we did human cadaver studies and we're looking at the structures of the body. These layers would have been thrown away, or a surgeon may cut through them not caring of what's happening in these layers. What we're saying with VFRT is these layers, this would be the lower adipose layer, brown adipose tissue, and these are the things that we think of as flesh, but we really don't think about what's happening in there. Since our cardiovascular and our lymphatic system and our nervous system is running through these layers, when things go wrong, we're saying that a lot of the problems are happening within these layers. Notice that this layer, the brown adipose layer, maintains some integrity. It has substance, it has volume to it, it has interstitial fluid from our cardiovascular system running through it. And the white thing that you're seeing on top of that, this is actually adipose tissue that is upside down. So these would be the layers here, this layer right here and that layer right there. There's actually layers of collagen fibers, and we were able to see how thick these were. These are just fibers that are oriented in a certain way. But when I talk about collagen fiber layers, this is what I'm talking about. These are the sliding layers that we very rarely get to see. This, since it's upside down, the next thing that would be laying up against these layers would be your muscles, your muscle groups. These are the outer layers surrounding your muscle groups. And they're very important. They're collagen fibers, they're collagen sheets, and they're meant to be able to slide past each other using hyaluronic acid and things of that nature. But then things get stuck in there, and you can start to see, in fact, I wish I hadn't have messed this up and drawn over it, but right where I'm circling, you can see that there's a bubble forming here. And this tends to happen with the interstitial fluid. That's interstitial fluid will compress and bubble up, and it's supposed to be, the interstitial fluid is supposed to be inside of these layers, and they're supposed to be even as it comes out of the cardiovascular system. It should be dispersed evenly so that there's no pressure variances within those layers. But when they get pulled out of the gel that's in there and they start to create these free-flowing fluid bubbles, then you have problems. There's where more hydraulic type of pressures are happening in these areas, and there's where you start to have problems. And you see that in VFRT. We can feel that, and we can actually use the tuning force to diffuse these free-flowing fluid pockets, diffuse them into other layers so that we can push them out and make sure that there's no fluid pressurization anymore. So that really is at the key, a key component of vibrational fascia release. where the vibration itself from the tuning fork and the stretching of the collagen fibers really go a long way to changing the entire environment that you're seeing here. So what is an adipose, a fat cell? So this particular adipocyte is a fat cell, and really this is the one that most people think of when they think of fat. It's in a bubble. You can see that the nucleus has kind of been forced to the outside of this fat cell. This is the cell itself. Its whole purpose is to be fat reservoir and have things like triglycerides inside of it. It's our ability to store energy, and when we need that energy to feed our cells, then there's a reverse process to be able to remove it from these fat cells. The problem is that when we as humans intake more energy, and there's a process to store that energy, these adipocytes get bigger and bigger and bigger and bigger, and when they can no longer stretch to accept more triglycerides, then more of these adipocytes will actually create themselves, and this is how we get fatter and have more volume to our body. But it's not all fat cells that are growing. There's fluid problems that we're going to show you. That's part of what we do with BFRT. The ability to get the triglycerides outside of these cells, we've actually figured that out with the tuning forks, using tuning forks to vibrate. And vibration from the tuning forks actually diffuses, and that word means that fluids from one side of a barrier can diffuse through a layer to allow things like the triglycerides to move out of those fat cells to be diffused through the walls of the adipocyte. So it's nothing more than just a bubble that has triglycerides in there. This is specifically the white adipose tissue, just made up of bubbles like that. What you're seeing here is a cross section that is the white adipose layer. So this diagnostic histology slide here gives you the ability to see based off of color. So there's a dye that's put in here that the pinkish reddish colors are able to show you. Those are where fascia is. So whenever you're seeing pink, you're seeing fascia tissue, fascia fibers that have been collected together, and they do certain things. They're creating compartments in here. This is probably one of the biggest things to understand, is the whole compartmentalization. This again is your outer adipose layer, just underneath your skin. You'll notice here that you're creating walls here. These are actually called lobules. So if I draw, maybe I should change the color here, but just to show you here that this is considered a lobule. It is individual fat cells, these white things here, individual fat cells, but they're also compartmentalized themselves. They're walled off by collagen fibers. So this is happening just underneath our skin. You can also see here, which is very interesting, you can start to see patterns here. Like, what are these things doing? These fat cells doing? It looks like they're kind of sequestered away from everything else. So the more dense the layers are, well, maybe I should change the color here. I'll change it to blue. The more dense these layers are, you can see how the tissue and the adipose cells are kind of living together, but when fluid starts to build up in these layers, there's a problem. It's very difficult to get the fluid out of the layers. Remember that your nervous system is running through this as well, and things getting pinched off, and you having flow problems with your cardiovascular system, and the ability for the lymphatic system to remove the excess fluids. There's a problem in these layers. And the fat, sometimes the fat cells, as they get bigger and bigger and bigger, that does create a problem. I'm going to show you a couple slides here in a minute that kind of make my point here. But just understand that what I'm showing you here is these fat cells live inside of other bags. We sometimes think of fascia that were bags within bags within bags. And we can also think of what I have here is this kind of a representation. You can see the different color balls in here. Those are representing the fat cells, and they are inside of what would be considered a lobule. So it's just a bag that keeps those fat cells together. And of course, each cell, as you saw in one of the very early pictures, those fat cells were kept together, held together, even though there wasn't the outer coating, a lobule. So these are all created by collagen fibers as well, maybe a different type of collagen fiber. So as you see on the image behind me, you can see how these things are kind of walled off into a lobule, and you can see that as this stretches, the fat cells themselves still stay within a compartment of a lobule, and those lobules are always moving and stretching and compressing. But the thing is that when I have gel inside of here, which is a component of these layers, you're not seeing the gel, but it is very apparent. Proteoglycans is what we think of, that's a gel inside of here that creates part of the structure too, but it also allows the fluid that comes out of the cardiovascular system flowing through here. When the plasma comes out of our cardiovascular system, it needs to feed the fat cells, it needs to feed all of the components that are within these layers, and it kind of trickles through these layers. The proteoglycan gel that's in this layer allows for compression without creating more pressure. That way you can push against your skin just like I can right now, and I'm not hurting when I push against that. Why is that? It's because the gel itself allows for the ability to maintain the same amount of pressure within this fatty space without having additional pressure. The problem is that when you get things like this ball right here, actually has some problems with it. You can see, you might be able to see this, that there's an empty space here. You got the balls themselves that are moving around here, but then the gel itself, the fluid, the cardiovascular system, the interstitial fluid, the plasma coming out of your cardiovascular system has kind of pulled itself away from the gel itself, and then you have these spaces, these pockets of interstitial fluid that is free flowing. So in these superficial adipose layers, there should be no free flowing fluid. When it's free flowing like this, now you're dealing with a different sort of pressure, hydraulic type of pressure. There is more pressure inside of this ball right now because of the fluid that's been pulled out of the gel that was originally designed to be able to squeeze and have pressure, or squeeze and change the volume without changing the pressure. Free flowing fluid spaces like this, interstitial fluid, there's where our problem is. We actually think of that free flowing fluid as edema. And in VFRT, what we've determined working with our clients is that we're all in some sort of localized edema. I'm going to show you some slides here in a little bit about where anytime you have a lot of fat cells that are getting larger and larger, and we start to get a little more obese, obviously we stop moving as much. There is a problem with the interstitial fluid. We have an edema-like state. We're never aware of these things. We can't measure fluid. We can't see fluid when it's happening. We think that we have a problem sometimes where there's a lot of pain and the doctor can't figure out why there's pain, and we go in for a surgery. Well, guess what happens when you go in for surgery? You cut through these layers, the fluid pressure is released, and a lot of times we think the surgery is the resolution to it, but when we open up those spaces to find out what's going on, we end up releasing the fluid pressure. Then what usually ends up happening later is you stop moving that part of your body because you had surgery and you're recovering. more fluid builds up, and eventually you get a reoccurrence, more fluid that's been pulled out of the gel that's in there. So it's kind of a reoccurring theme for us. VFRT for us is about that fluid that is edema-like. We usually think of edema as extreme, like lymphedema. So, you know, a person's entire leg is filled with fluid. We're still talking about the exact same mechanisms here. We still need to get the fluid out, and that's normally done through the lymphatic system. But when the lymphatic system gets compressed in these pressurized areas, how are you going to get the lymphatic fluid out? Actually, I say lymphatic fluid, but how do you get that same sort of interstitial fluid, the plasma that's in these spaces? How do you get them out of the spaces when you've compressed the vessels that try to remove it? So that's another thing to consider. All right, so what you're seeing on this slide is that deeper brown adipose tissue. And what I'm showing you is a cross-section of the brown adipose tissue. So all of the little fat cells are inside of there. But notice that there is, so this is the actual brown, the entire brown adipose tissue. And there is a very distinct layer here and a very distinct layer here. And all of the brown adipose tissue is basically in between those layers. So it may look like it's a thick layer and a big old blob laying on the glass table there. But if you look at the cross section, you can see that there's a sheet of fascia that's the bottom barrier, and then there's a top barrier. It's a so if those collagen fibers have oriented themselves, they become the barrier to hold the fat cells together. And it's very difficult to see, but what you're seeing here is adipose tissue and gel. It's actually a substance. You know, this cow is no longer alive anymore, and it's very difficult to see what's going on in these layers right here. It's very difficult to see the fact that there is some substance to there. It's not just open space and fibers. The fat cells themselves, there's gel in there that stays there. The only reason, you know, we usually don't see this kind of stuff, maybe in more fatty kind of stuff. We usually try to remove the fat when we're eating cow products or chicken or pork or something like that. We usually try to get rid of as much fat. This is the fat that we're getting rid of. But the problem is that in humans, there's problems here with these layers. There's still cardiovascular stuff running through there. There's still fluid inside of these gelled layers, and when they get too much fluid in there, there's nowhere for that stuff to go, and that's where we see a lot of the problems. The collagen fibers will actually try to reorient themselves around this free-flowing fluid that is trapped in there. Another thing I'd like to show you here is you see that there's a layer here that's removed itself from this top layer. So there are layers upon layers upon layers. You're seeing one very large layer, and then you're seeing that there's other layers underneath it that, again, there's going to be a sliding component associated with these layers. So this is the brown adipose. And this is what the brown adipose layer looks like. So I showed you what a white adipose tissue looked like, and that was just basically one big ball, and it had the nucleus was kind of shoved to the outer edge of it, and there's just one big old thing, ball or balloon that held triglycerides in a semi-liquid state. In brown adipose tissue, notice that you have all these little tiny droplets. So we still have, let me try this again. Oh, let me go back. we still have our ability, our little droplets here. These are inside of larger cells. So we still have the nucleus right here, and then we have little droplets inside of here. So different purposes for these deeper layers. This is a layer that would be just on the outside of our muscle layer. We call this brown adipose tissue, and it's still the same sort of functionality. These are a little more long-term fat cells, and they're used for slightly different reasons. And it also, of course, is seen as a cushion for any impact that we might have on the outer part of our skin. But brown adipose tissue, still the same type of concept, only there's just little itty-bitty droplets of fat inside of these. All right, so what you're seeing here is a cross-section, another histology slide, and a couple things that I want to show you here. What I'm showing you here with this slide is all the different things that live within this outer superficial adipose layer. These are the white adipose cells, and you can see that the white areas are adipose cells. Then here's our other players, or other inhabitants of that superficial adipose layer. Now, what I'm about to tell you is just based off of, since I don't look at these histology slides all the time, I could have these things a little bit, I think that I'm naming them correctly. There is the possibility that someone could come along and say, well, no, that thing that you're pointing at is probably this, this, and this. What we do know, or what I think I know, these are the lymphatic vessels, and the things that the information that came with these particular images had also identified these things as well. Since this is a histology slide that is part of immunostaining, that means that the substances they use in the stain allowed certain things to show up, and the little dots that you're seeing inside of the lymphatic vessels are the lymphocytes, and you're going to find dots throughout these that might be cells or specialized cells that the dye that they used is going to make it appear as contrast to white. And we know that right now that white is more fluid. Not only the triglycerides, and if you were to zoom in, you would see the cells that are supporting the fat cells. But what I've circled in blue, not counting that adipose tissue right here, or the adipose cell, but everything else that I've highlighted in blue, those are your lymphatic vessels. Those are designed to take this fluid that you're currently not seeing, that is dispersing itself through these fat cells. The fluid itself, the interstitial fluid, is coming out of the cardiovascular system. Very specifically, it's coming out of the capillaries of the arteries themselves. Well, where is the artery? This is an artery right here. The reason we know that's an artery is because of, well, here's another artery. Arteries have muscle cells. They're designed to flex and have volume, to maintain its volume as much as possible. Most of the time when we see a cross-section of an artery, it does have does maintain its round shape very well. And of course you can see the blood that's inside of the arteries. There's an interesting thing happening on this histology slide here that actually is pretty important to what we're looking at. When things go bad in this layer, we do have an artery that is starting to be squished. That's pretty important, because when you start to compress our arteries, especially down where they're very small like this, we have arteries down to a cellular level. Remember, we're seeing fat cells at the cell level. So these arteries have gotten smaller and smaller in diameter, and now they're in the space of cell size diameter of the arteries. where they actually have capillaries inside of their walls, and they're trying to get the fluid out into the space, the plasma out into the space to feed all the inhabitants of this space. What you're seeing right here is a vein, and notice that the vein does not have as much of an outer structure layer, the muscle cells. There's fewer muscle cells in a vein, which makes them very susceptible to collapse, especially when you start to compress them. Notice that that vein itself has a very elongated, looks like it's squashed. Now, because we're looking at an exact cross section, it is possible that these things that look squashed, it might just be the angle that we're seeing them. Maybe it's a little more of an angle that these things are appearing in. Since we're looking at cross section, it might look a little different. However, I don't think that it's just the angle that we're seeing them, because you're seeing in the same spot an artery over here, and then you're seeing these lymphatic vessels, which do not have a lot of the same support mechanism itself. When they get under pressure, they collapse as well, just like you see what's happening here. And then, of course, you get another vein that's right here on the bottom edge. Now, the reason why I think this is pretty important is because when things go wrong, here's what we usually end up seeing. What I'm noticing here is a line of something that's happening here, where some tension, some scarring, something's happening with our fascial system that's supposed to control this space and keep it up and open and keeping things flowing. That there's some edema that's happening here that could be problems. I can definitely see a line of something that's causing everything to kind of be moved towards that green line. So that could be just temporary movement, or it could be that there's a scarring of some sort, or it could be that this person is in a postural position and sitting and having something weighing on it, to where the brown adipose tissue is just kind of pushing everything in, and you're compressing your arteries and veins, and oh, by the way, these are most likely nerves right here. They're all in close proximity to each other. They need volume, and they need to maintain that volume, and sometimes that just doesn't happen. One of the things I'd like to take note of up here, coming out of the artery, there's this area right here. It looks like a lot of things happening here in larger white areas. Way down in the bottom left-hand corner here, there's another area that looks like there's no adipose cells to there. What that is showing me, and there's some other areas in here too, what that's showing me is that's free-flowing fluid that should have been part of the gel that's running through this layer. And again, when the fluid, the interstitial fluid coming out of the cardiovascular system starts to pool in certain areas, it's not part of the gel. It actually separates itself from the gel. When we have those problems, that's what edema really is. At a very, very localized level, you're seeing very micro view of what's happening underneath our skin. And we very rarely get a chance to see that. We have all the inhabitants of our superficial layers, and they interact with each other. When we compress the layer, when we have scarring, when we fold layers, when we sleep at night and compress layers, we have problems. We have fluid that gets pushed out that shouldn't be coming out of these the arteries. We have fluid that gets maintained and pressurized inside of compartments that can't move into the next compartment. When pressurization happens, it presses against our nerves, our nerve endings, and we have pain. We have pain usually associated with localized edema. All right, let me get into the next slide here so we can finish out this training video. What you're seeing here is a much closer look at the artery, which is on the right, and the vein, which is on the left. You notice that the artery has that thick, darker ring around it. This is another immunostaining process. So the artery itself is supposed to, again, maintain as much as possible, maintain a nice round structure. And of course, there's a lot of pulsing that goes through there. There's the heart is beating, and so there's pressures. The artery needs to stretch and then return back to its original roundness. And so we have a lot of fat cells, or not fat cells, but muscle type cells that form part of the artery itself. So it has the ability to maintain its tensional integrity. And then on the left-hand side, you see the inherent problem with veins themselves. Why we have venous insufficiency, why we have veins that have the inability to bring that fluid back up to the heart as a closed loop. That when we have problems with, when we start to pressurize these spaces, we have problems with too much fluid coming out of the arteries. We have problems with veins not being able to return the fluid back to the heart. Fluid that's not inside the gel creates problems. It creates fluid pockets. If we're looking at an immunostained situation here, and if these are the actual, if what I'm seeing here is still the same sort of immunostaining, then what that's telling me is that all of this area here, if everything is right, all of this area here that I'm not seeing fat cells, which I am in fact seeing them up here, if that's all free fluid spaces, that fluid there itself is not gaining the benefit of pressing against these spaces without having more pressure. And anytime fluid gets released from that gel, that proteoglycan gel, you have problems. You have hydraulic sort of pressure pushing against everything that's inside of that space. This slide here is just another way of looking. It's a much closer look at an artery. You can see these individual muscle cells. And if you were to look at muscle cells underneath the in a histology sort of immunostaining view, you would see the same thing, where it's a striated sort of look there on that inner ring. So that's how we know that our arteries have very thick layers of muscle as a part of the vessel itself. So this image here is just showing you and reminding you that, let's say the red thing that's moving through the adipose layer, they have to occupy the same space as the adipose cells, which you're seeing are the different bubbles that you're seeing in the picture. So as the adipose start to fill up more and more with triglycerides, as our fat cells start to expand out, our body will respond accordingly over time. But if it's so rapid, you're starting to compress the cardiovascular system, which really, in my opinion, starts the whole cycle of things going wrong in that space. The spaces in between the adipose layers, that's all got gel inside of it, even though you can't see it. The fluid, the interstitial fluid, lives in the same space as the gel. The fluid, the plasma that comes out of the cardiovascular system, they live in the same space. But remember, again, you can press on those spaces and not have more pressure. That was a very important part of the gel, to make sure that there's no added pressure when you press against them. That way, if that was true, then every time we moved or every time we touched our skin, we would feel pain, because there's pain receptors in those spaces as well. So we want to keep that fluid inside that gel. Once it's removed from that gel, now we have to get it out of the space. The main removal mechanism for pulling interstitial fluid out of those spaces is the lymphatic vessels. Unfortunately, the lymphatic vessels, the intake part of those vessels get compressed, and you have a very difficult time getting the fluids out. What you're seeing here on the screen is is part of our research, where we were actually able to take what you're seeing on the right hand side there is is the tuning fork. So right here, everything over here on this side is the tuning fork. So we actually, I struck a tuning fork. You can see that's the entire stem and the base of the tuning fork pressing against the adipose tissue of the sample that we had. And what you notice right here, this is the very interesting part of it. What we were trying to see here in a live environment, and we did get this on video, is that when the tuning fork presses against the skin, and of course this is the cow, not a human, but the same thing we're seeing in VFRT with fat reduction, we were able to do what would be considered, we call it fat burning, but really what we thought was happening, we're able to see it right here. The brown things that you're seeing, the brown fluid, we believe that to be the triglycerides being released or diffused through the adipose cells. The adipose cells you're actually seeing on the left-hand side, and I believe that's probably the brown adipose tissue. And you're seeing the substances come out of those fat cells. And that doesn't happen just on pressure alone. If we were to take a tuning fork and put it right on those cells, the only thing that comes out is the clearer liquid, which is the interstitial fluid. And it's not until there's a vibration involved in there, striking the tuning fork and then placing in the same spot, do you start to get the colored liquid, the brownish colored liquid coming out and mixing with the interstitial fluid. So our theory was that the tuning forks were able to diffuse triglycerides through the fat cells, meaning that we can work on very, very targeted parts of the body and target the cells to release their fluids on demand. So anything that's having pressure from the tuning fork, which is pretty important, and the vibration from the tuning fork allows that diffusion to happen. There has to be a compression part of it, pressure. There has to be a vibration. Those two together was our concept and what we thought was our theory, and we're actually, what we believe here on our video, or on our still shot of our video, was that we're actually seeing that play out on the video itself. So that would be the triglycerides being released from the fat cells. And we also believe that the same sort of thing is happening when you're taking the fluids that get trapped within those spaces, that when you press down with the tuning fork and it's vibrating, you're actually allowing that fluid to diffuse from one pressurized space into another space, thereby relieving the pressure and relieving the pressure on your nervous system and restoring some of the flow, the blood flow, and back to the cardiovascular system. All right, this slide is showing you the different layers. It's another immunostaining. So at the very top layer, we see the skin itself. I've already showed you something similar to this a little bit earlier. So top layer of the skin right here. And what's really nice is that we're able to see how the different layers here are we're able to see how the different layers are in the skin, or just underneath the skin. Now we're zoomed in quite a bit here, where this top layer here, we're probably still talking about the outer dermis layer, and then it most likely starts to transition right here into the the epidermis layer. The dermis layer itself is starting here, and then you see the fat cells start to display themselves about right here. You start to see a lobule happen at the very bottom here. But as we're looking at these histology slides, something should be very apparent to you, is all of this white area right here and here and here, and there are also layers there. They're sliding layers as well, and if you consider the fact that all of the white areas that are not inside of bubbles are interstitial fluid that's removed themselves from these confined spaces, they make their own confined spaces. There's layers of fluid happening there. We were able to see in medical literature where there's a declaration in medical literature saying that when there's an obese person that has fat cells that have grown beyond normal, then you see localized edema, and that's actually what you're seeing here. Now this is taken, you have the paddle, because you're looking down through a slice of the skin. You do have some pressure from the outer paddle when you're taking these the diagnostic images here. And as it's traveling through each of the layers, you're able to see the density of that immunostaining. So, there is some compression there from the outer part of the skin, and from the ultrasonic paddle, of course. But think about a tuning fork that's been placed on that skin. You're starting to press down on these layers. You're starting to compress them, but you're also getting vibration going through these layers. And sometimes where one layer of fluid cannot escape because there's some fascial, there's like the lobules that you have to move through a layer of the outer lobule, then it has to move through another fascial layer, and then there's thicker layers. There's all kinds of layers there, and some of them create their own compartment. And when fluid that's under pressure, like interstitial fluid outside of the gel, when they start to pressurize, the hydraulic pressure, that's where the pain comes from. That's where the immobility comes from. Those are the things that really get forgotten in things like physiotherapy and massage and things like that. Healing modalities that do not consider the fact that fluid gets pressurized in these spaces, and that's where a lot of our pain comes from. We really need to consider the fact that that fluid needs to be diffused into a layer that can disperse it out. When we're doing things like pressing down, when we're giving massages, a lot of reasons why they feel so good is you can press down on the skin and stretch the fibers and create more volume. Cupping creates more volume. Taping creates more volume. But it doesn't necessarily get rid of the fluids that are trapped in the spaces. When a tuning fork presses against the skin, stretches the fibers, it diffuses fluids that are trapped in those areas into the next area, and it might be into a deeper layer where you can press and push it out. You can push those fluids out into other areas. Let the lymphatic vessels that are able to operate unpressurized, let the lymphatic vessels pick it up and pull that fluid out. So that has a lot to do with VFRT, is using the tuning forks to their advantage. Stretch or pressure and vibration are the two things that are really needed to change the environment. It's not only changing the cells themselves, it's changing the way that the collagen fibers can remap themselves and reconfigure themselves. It's changing the way the fluid pressure pockets are able to move away from those pressurized areas and take some pressure off of your nerves. And then one last thing that I want to show you in this this video here. All right, let me see if I can get. Oh, let's go back one slide here. Finish this up. Okay. One of the things that I want to talk about here is what happens. We know that bones have osteoclasts that will create more dense structures. You'll have more bone density that's based off of pressure that's happening on your bones. That the osteoblasts are designed to lay more bone down, or more bone structure, or more dense bone structure based off of pressure. And that the osteoclasts are designed to actually eat away bone structure or dissolve it. The same thing is happening with our soft tissue, the fascia fibers. Even though we usually don't use the word fibroblast to talk about how structures, fibers, collagen fibers like this, how they're actually reduced. Like if I don't need this fiber anymore, sometimes these collagen fibers stay in the form of adhesions and scars, and they're not in a they're kind of wound up and they're not quite doing anything. The problem is that this collagen fiber that just wound itself up, it doesn't have the capability of knowing to destroy itself. And there's where we have long-term adhesions and scars that we never get rid of. The functionality that actually happens here with taking this fiber and making it dissolve itself, there is a function here where if it's not needed anymore, there's no more tension on this fiber. And this is more of a longer term type of thing, but the fibers themselves start to unwind when they're not needed anymore. And what that does is it leaves these individual parts of this triple helix very vulnerable to collagenase and certain substances that are designed to snap these fibers in half once there's an unwinding. This is a very well documented, researched thing where collagenase is the substance that is actually able to snap these in half and cut these individual bonds in this fibril so that that collagen can go away. So where it's very difficult to understand the mechanisms to take collagen fibers and have it remap itself, it does that all day long. There's a time factor, though, involved in that. Individual fibers always remap themselves when they're under the right conditions to separate and allow collagenase to dissolve or cut it in half, and then it comes back, it gets reused. The substances that built that fibril get reused. But we have to consider the fact that that it takes certain commands. Some people in physiotherapy believe that fascial adhesions are impossible to remap or to resolve because it takes so much time to have that tension on that collagen fiber to allow it to dissolve itself or to die. And what happens with a tuning fork is that the oscillations in a tuning fork under pressure, so if I strike it and I'm putting it on the skin, when I have it under pressure, that actually causes the programming to listen for a new command. Remember that stretch and vibration are the two things that cause cells to change their command or do something different. And it also applies to the fibroblast itself, and it applies to the fibers themselves. Pressure is needed. Vibration is needed. What we see with VFRT is that when vibration, oscillation under the same conditions, I have the same pressure right now, I'm giving all the fibroblasts underneath my my tuning fork a repeating command over and over and over again. And sometimes that command, if we can get it right, sometimes that command is to change what it is you're doing. In the meantime, we're also taking the fluid pressure that's happening right underneath the tuning fork and releasing that pressure, so you also have a change in the environment. The vibration from the tuning forks is actually causing a speeding up of what would happen normally, where things happen within our body, commands that are given to do certain things. What we found is that the tuning fork vibration actually speeds things up. It speeds up healing. It speeds up the healing process. When you have a cut and the inflammation and all of that stuff, we can actually speed up these processes. So sometimes it happens within a couple tuning fork placements. Sometimes it happens within a session. Sometimes, like a bone break, if we start to get the fluids away and introduce vibration with the tuning forks, you'll actually see the speed up of the healing. Even in a burn, like when you get burned on something like a pot on the stove, if you were to apply the tuning forks directly to that burn as it's happening, you can actually speed the entire process up and actually shut down some of the processes that are happening, to where you would think that, okay, so now it's going to be a lot of pain, I'm going to have damage to the cells, I'm going to have scarring. All that stuff can actually be taken away if you get to the tuning forks, you get it onto that burn area, immediately it speeds up the entire process and can actually completely stop the destructive process that goes along with burns, to where you wouldn't even notice that anything even happened if you can get to that burn immediately with the tuning forks. So it does speed up the process. That vibration is a command, and the pressure is also a command or a condition. So that's one of the things that we consider in vibrational fascia release technique. It's fluid, it's fascia, it's understanding the body from a completely different aspect. And the things that you just saw are the things that we live with in using tuning forks, and understanding that vibration can have an effect on these things. We just need to look in the right area. We need to think the right things. We need to see the body in a totally different way. That there's fluid involved in it. There's pressures involved in it. And then fascia and fluid themselves together really control a lot of what's happening with mobility restrictions and pain. And those are things that we can usually resolve within one session with vibrational fascia technique, release technique.